Hi, welcome back. Let's see some other interesting feature of Nether's theorem. Nether's theorem says that for each symmetry of the Lagrangian there is a conserved quantity. Remember that symmetry here means that if we change the coordinates by some small amount, the Lagrangian does not change at first order in that quantity. Let the Lagrangian be invariant to first order in the small number epsilon under the change of coordinates q to q plus epsilon times k of q. Each k of q may be a function of all the coordinates k sub I, which I collectively denote by just q. The fact that the Lagrangian is invariant, that does not change at first order in epsilon, means that its derivative with respect to epsilon is zero, which mathematically writes as we can use Lagrange equations to rewrite all this as but this implies that what we have inside the parenthesis is conserved, thus not changing time. We define P of Q and Q dot as the conserved momentum. And look that it does not need to have units of momentum. This could be a familiar quantity, yes, but it could be something else, some combination of coordinates and velocities. Let's see an example. Let's consider the following Lagrangian. If we make transformations of x going to x plus epsilon and y going to y plus 2 epsilon, and we see that the Lagrangian does not change. It is, in fact, invariant to all orders of epsilon. Then we can write the conserved momentum as this. But look that despite the three factor, these are simply the x and y components of the linear momentum, which each one of them is conserved. May the science be with you.